The next important theorem related to this chapter is Gauss's theorem. It is very important for you. Gauss's theorem means the electric flux produced at any point near to a point charge, that is usually represented by here phi, then electric flux is equal to the closed integral AdS. The definition of this one is the electric flux produced by a point charge in any closed surface is equal to 1 by epsilon 0 times of the charge enclosed in it. In it here means the charge is always placed in a closed circuit. The charge is always placed in it. That is the meaning of it. The flux produced by that particular charge is here represented by phi. Then phi is equal to the closed integral E into ds. Here ds is also a vector quantity. Then electric flux can be calculated by using this equation. Phi is equal to closed integral AdS, where E is the electric field intensity and integral ds means the total area of the closed surface. This is the definition. Electric flux phi is equal to closed integral AdS, which is equal to q by epsilon 0, where q is the charge associated in the given closed surface. And this is the definition of electric flux. Electric flux phi through any closed surface is equal to 1 by epsilon 0 times of the net charge q enclosed by the surface. That is very important for you. And this equation is also important for you. This is one of the application to find the electric field intensity at any point near to a long straight wire. It is also called a line charge, and the electric field intensity at any point near to a line charge is given by lambda by 2 pi epsilon 0 into r. Otherwise it can be written as 1 by 4 pi epsilon naught into 2 lambda by r. This is very easy to find the electric field intensity due to a line charge, because 1 by 4 pi epsilon naught is equal to 9 into 10 raised to 9. So this equation is used to find the electric field intensity due to an infinitely long straight wire. That infinitely long straight wire which carries an electric current, therefore this conductor is also called line charge. And also we have to find the electric field intensity at any point due to a thin infinite plane sheet. The equation is E is equal to sigma by 2 epsilon 0. For example, this is a plane sheet. Then we have to find the electric field intensity at any point very near to this plane sheet. Here sigma is the surface charge density. Surface charge density means the charge per unit area. The total charge per total area is equal to surface charge density. That means the charge per unit area is called surface charge density. That is given by sigma. Then sigma by 2 epsilon 0 can be used to find the electric field intensity at any point, say P, near to this plane sheet. It's an important equation. Sigma by 2 epsilon 0. And another important relation is, let us imagine two charged plates. The electric field intensity in between two plates is given as sigma by epsilon 0. That means here there is a difference. The electric field intensity produced by a single plane sheet is sigma by 2 epsilon 0, and the electric field intensity in between two metal plates is given by sigma by epsilon 0, and this equation is very important by calculating some problems. So this is an important equation. E is equal to sigma by epsilon 0. Then electric field intensity due to uniformly charged spherical shell then that can be calculated by using using an equation E is equal to KQ by R square. Here K is equal to 1 by 4 pi epsilon 0 into Q by R square. Here R greater than capital R. So what is the meaning of it? For example, this is a spherical shell and let capital R is the radius of the shell. So here we have to find the electric field intensity outside of the shell. So first of all, we draw a Gaussian phase around the surface. Then the radius of the surface is small r. And here we can see that small r is greater than capital R. So the meaning of this one is, now we have to find out electric field intensity at a point outside of the conducting shell. This is a conducting shell. Let O is the center of the sphere. And the electric field intensity inside the conducting shell is always equal to 0. This is because the field is usually produced by the presence of electric charges. There is a platform which is required to stay the charges on the surface. That means here there is no platform, inside there is no platform, and as a result the value of Q is equal to 0, and therefore the field intensity is 0. Here there is a platform, the charges are always residing on the surface. That means intensity is maximum on the surface, and as it goes out, the field intensity gradually decreases, inversely proportional to square of the distance. So this is the first case. In the first case, the electric field intensity is given by 1 by 4 pi epsilon naught into Q by R square. This is the field intensity at any point outside the conducting shell, and inside the shell there is no platform for the residence of charges, and as a result Q is equal to 0. So intensity is also equal to 0. And on the surface there is a platform is there. The charges are maximum residing at that region. So the intensity is maximum on the surface. The value is given as intensity is equal to 1 by 4 pi epsilon naught into Q by R square, where capital R is the radius of the sphere. That is given in your pages. Here E is equal to KQ by R square for R greater than capital R. Here small r is the distance between the point P, which is situated outside of the sphere. Therefore, here it is written as R greater than capital R, where capital R is the radius of the sphere, and R less than capital R, you know that the distance is less than capital R. There is no platform. Here Q is 0, therefore E is equal to 0. And on the surface, the maximum charges are residing on the surface, though the field intensity is maximum on the surface, and that can be written as K into Q by capital R square. That means here the point P which is lies on the surface. Therefore, here small r is equal to capital R. The value of K is always 1 by 4 pi epsilon naught.